Hello friends, I am going to take your second lecture regarding the digital logic families. To start this second lecture, we will understand how the BJT and the MOSFET work as a switch or two-state devices, BJTs. The bipolar junction transistor BJT is available in two polarities, NPN transistor and PNP transistor, as shown by the symbol in figure 14.4a. The BJT terminals are named as collector, emitter and base as indicated in figure 14.4b. The BJT behaves as an electronic switch. You understand, this is NPN transistor. This N-type material is a collector. This is also N-type material which is called emitter, and this is P-type material which is sandwich between two N-type material which is known as a base. So there is one junction between base and emitter, there is another junction between base and collector. So you can think about this is that there are two diodes, base emitter diode and base collector diode is there. So both this diode are going to be forward bias, then the transistor will be in a closed switch, and if both the diodes are in a reverse bias, the transistor will be in open switch. So this transistor is acting like a switch. This is NPN transistor and another one is a PNP transistor. You know about all these things. So normally the switch between collector and emitter, either it is going to be open or it is going to be closed, and it is working as a two-state devices. All digital devices are having either on or off, only two value problems are dealing, and hence the transistor is operating either in a cutoff region or in saturation regions, so of the load lines. That's why it is working at two distant points of the load line only, and that's why it is working as a switch. If the transistor is at saturation, voltage across this collector and emitter is approximately 0.2 volt, which is corresponds to low level. And when the transistor is off, it is open switch and the voltage across collector and emitter is approximately equal to VCC, that is going to be high level. So this way it is working as a switch or it is working as a inverter that you have studied. If the transistor is conducting in NPN type transistor, the direction of the conventional current is from collector to the emitter, and for the PNP transistor it is just opposite to that. It shows by this arrow, that is a conventional direction of the current is shown here. So this way it is working as a switch. Now we will take example related this transistor as a switch, so you will understand better way. Example number 3. Determine the current I and the voltage V2 for the circuit in figure 14.5a. If the input voltage V1 is equal to 0 volt DC and if the input voltage V1 is equal to plus 5 volt DC. Repeat the part A for the circuit in figure 14.5b, that is for PNP transistor. We will see the circuit. The switch is activated by applying voltage between base and emitter. Here is how it works. The voltage between base and emitter is going to be 0. That means base emitter junction is the reverse bias. So there is no base current and hence there is no collector current and the switch is open. The switch is open and no current allows between collector and emitter. The transistor is off. Voltage is applied between the base and emitter. That means base is positive with respect to emitter. Then you can say that that diode is forward bias. There is a base current which will be multiplied by HAP and that is called collector current. So the voltage is going to be dropped across RL, ICRL, and the voltage across the transistor VCE, that is approximately equal to 0.2 volt low, and the switch is going to be closed. The voltage is applied between the base emitter, the switch is closed and current is allowed between collector and emitter. The transistor is on. The voltage between emitter and collector across the closed switch is almost 0. This you can see in this circuitry. This is NPN transistor. So, the collector is given a positive terminal 5 volt with respect to emitter, that is the ground. If the input voltage V1 is going to be 0, that means base emitter junction is reverse bias and there is no base current, so there is no collector current, ICRL is going to be 0, so that same voltage is going to be appear over here. So, 5 volt will be appear at here and V2 is equal to 5 volt. And if the V1 is equal to 5 volt, that means base emitter junction is going to be forward bias. So, base current is there, hence it will produce a collector current, and because of that the voltage 5 volt will be dropped across this resistance ICRL. So, here the potential is approximately 0. So, input is low, that is 0 volt, output is going to be 5 volt. Input is going to be high, that is going to be 5 volt, then output is going to be low, that is going to be 0 volt. So, this transistor is working as a NOT gate or inverter. The same thing for the PNP transistor. Here the emitter is here plus 5 volt and the collector is connected with the grounds. Polarity is just opposite to the NPN transistor. Here there is emitter resistance is there between collector and ground, there is a 1K resistance is there. So, if Pi is going to be 0 volt, that means the base potential is lower than the emitter potential and thence this diode is going to be forward bias, there is a current and ICRL will be there, that is why the V2 is going to be 5 volt will be there. And if Pi is going to be 5 volt, that means base and potential, base and emitter are at the same potential. So, the potential difference is going to be 0 and hence it is reverse bias, no current will be flowing and hence the voltage across this resistance is going to be 0. So, V2 is going to be 0 and it is inverted. So, in both the cases it is working as a NOT gate or inverter. Let us look carefully at the result from the example 14.3. For both the circuits, when V1 is equal to 0 volt DC, V2 is equal to 5 volt. Also, when V1 is equal to 5 volt, V2 is equal to 0 volt DC. Clearly, V2 is always inverse of the V1. In other words, each circuit in figure 14.5 is an inverter. Either of this circuit can be used to implement the basic inverter introduced in chapter 1, or here the transistor is working as a inverter, BJT is working as a NOT gate. Now, similar things we are going to see for CMOS circuit. CMOS, there are two types of the CMOS there, N channel MOSFET and P channel MOSFET. When they are working as a complementary, then it is called CMOS, complementary metal oxide. This chapter is actually we have taken from the Malvin-Leach itself, but this particular pages I have taken from 4th edition, which is not available with the market. So, I have printed, but this is essential to understand that how the P channel and N channel MOSFETs are going to be utilized to prepare a CMOS technology. And that is why in certain pages I utilize from 4th edition of Malvin-Leach. In that one, that was a separate chapter, CMOS circuit, chapter number 7. So, understand these things. Complementary metal oxide semiconductor CMOS device are chips that combines P channel and N channel MOSFET in a push-pull arrangement. Because the input current of the MOSFET is much smaller than that of a bipolar transistor, almost 0, it is in nanoamperes. Cascaded CMOS devices have very low power dissipation compared with the transistor logic, TTL logic families. This is low power dissipation, or this low dissipation explain why CMOS circuits are used to in battery powered equipments such as pocket calculators, digital wristwatch and portable computers, etc. Where battery is used, the power dissipation is required less, where the CMOS technology is used, because in CMOS the power dissipation is very less compared to the TTL circuits. Remember, this is the advantage of the CMOS. MOSFETs. MOSFETs are available in two polarities, N-channel MOSFET and P-channel MOSFET, as shown by the symbol in figure 14.6a. The MOSFETs operate as a depletion type MOSFET or enhancement mode devices. The transistor in figure 14.6 are enhancement type. The MOSFET terminals are named as a gate, source and drain and body as indicated. Gate is just analogous to the base, source is analogous to the emitter and drain is analogous to the collector in a BJT. Remember. So, there are depletion mode as well as enhancement mode is there. Depletion type of the MOSFETs are known as normally on MOSFETs, which is utilized for analog electronics just like a amplifier etc. Oscillators or amplifiers or such kind of circuits, depletion type of the MOSFETs is utilized. But enhancement type MOSFETs are normally off MOSFET and they are going to be utilized in digital devices. So, here we are going to learn about the enhancement type MOSFETs only. What is enhancement type MOSFETs and structure and how it functions and what is the inversion layer, what is the threshold voltage and how the polarity is going to be connected etc. We are going to learn over here. This is very important, which is given in 4th edition only. That is why I have taken that pages over here. So, please read and study this very carefully. The enhancement type MOSFETs. The metal oxide semiconductor field effect transistor or MOSFET has source, gate and drain. There are two types of MOSFETs, the depletion type and enhancement type. Before we discuss the CMOS circuit, it may be helpful to review the enhancement type MOSFET because it is used in a CMOS technology. The structure of the CMOS or enhancement type MOSFETs, which is given in this figure 7.1a. This is N-channel enhancement type MOSFET. Similarly, there is a P-channel enhancement type MOSFET is going to be available. In figure 7.1a shows a N-channel enhancement type MOSFET. The P region called the substrate lies between the two regions of the material, N-type material. Free electrons can flow from the source lower N-type region to the drain, which is upper N-type region. A thin layer of silicon dioxide SiO2 is deposited on the left side of the substrate. Silicon dioxide is the same as a glass, which is an insulator. The gate is metallic electrode that controls the flow of free electrons between the source and drain. So, just like NPN transistor, this is also N-type semiconductor material. This is N-type semiconductor material. Between two N-type semiconductor material, there is a P-type semiconductor material is inserted or it is sandwich. And this P-type semiconductor material which is working as a substrate here. This upper N-type semiconductor material working as a drain and this lower one is working as a source. Here left side of the substrate there is this SiO2, that is silicon dioxide, thin layer of the silicon dioxide which is nothing but insulated glass is deposited, and then there is a metallic electrode which is working as a gate. So, between this metallic plate and this P type material, that is substrate, there is a insulator is there. So, it will work as a substrate and gate will work as a capacitor. Now, how it works and what is the inversion layer, that you have to understand. Normally, how the biasing of the circuit is going to be done? Substrate is connected with the negative terminal of the battery. You can see that the positive terminal of the battery VDD is connected with the drain, that is N-type material. Negative terminal of the VDD is connected with the source. N-type material which is having excess of the electrons, that is n type electrons will be there, which is supposed to move because of this battery force. The electrons should move from source to the drain. So that constitutes the currents from drain to the source, that is called conventional current. But because of the presence of the substrate, the normally if VGS is equal to 0, then electron cannot move from the source to the drain, and this is remains open. So it is called normally open switch between drain and source. So let us see. In figure 7.1b shows a normal biasing polarities. When VGS is equal to 0, the VDG supply tries to force free electrons from the source to the drain, but the P substrate has only few thermally produced electrons. Aside from this, minority carriers and some surface leakage current, the current between the source and drain is 0. For this reason, the enhancement type MOSFET is also called a normally off MOSFET. That is why this is working in a digital electronics. This is normally off MOSFET is going to be there. The gate and P substrate are like two plates of a capacitor separated by dielectric material SiO2 like this. When the gate is positive, it can attract enough free electrons from the source to form a thin layer of free electrons between the source and drain. The effect is equivalent to creating a thin layer of N-type material next to the silicon dioxide. This layer of the free electrons is called N-type inversion layer. When the layer of the free electrons appears, the current can flow easily between the source and drain. So when the gate becomes positive, VGS is connected here, battery. So because of this, this electrode is positive and this electrode, that is substrate, is going to be negative. So this will act as a capacitor between two conductor. There is an insulator, and just in this side, just this side of this SiO2, there is a electrons, that is negative electrons are going to be deposited, and they are forming here small layer, thin layer of N-type material, which is providing the path between source and drain, and because of that the free electrons from here can move from here to here, and drain current is going to be possible from drain to the source. So this MOSFET is going to be a closed switch, and the voltage across this closed switch is almost 0. The effect is equivalent to creating a thin layer of N-type material next to the silicon dioxide. This layer of the free electrons is called N-type inversion layer. When this layer of the free electrons appears, the current flows easily between the source and the drain. Now what is the threshold voltage? If VGS is going to be 0, there cannot be inversion layer. Here, if this VGS voltage is going to be 0, that means capacitor is going to be uncharged. There cannot be inversion layer here. There cannot be current. The MOSFET is going to be off. But when the VGS is voltage is going to be sufficiently large, so here there is a inversion layer is going to be created. So minimum VGS voltage where the inversion layer is going to be formed so that current is going to be established, that voltage is called the VGS threshold voltage. So the minimum gate voltage that creates the N-type inversion layer is called the threshold voltage, VGS threshold. When VGS is less than VGS threshold voltage, zero current flows from source to the drain, that means electrons flow. But when VGS is greater than VGS threshold, N-type inversion layer is connect the source and drain, and we get the current. The threshold voltage, VGS threshold, can vary from less than 1 volt to more than 5 volt depending upon particular device being used. That means in that N-type or P-type material, how much doping etc. is going to be used. Depending upon that, its threshold voltage can be changed from 1 volt to 5 volt. Now you can see that there are two symbols here, A and B. This shows N channel inversions layer is going to be produced. That's why it is called N channel MOSFET. And similarly, if instead of this, if there are two P channel MOSFETs, two P type of substance, P and P, if this kind of MOSFET is going to be prepared, then it is called P channel MOSFET, because here the supply is going to be reverse. Instead of positive terminal to the drain, negative terminal to the drain is going to be connected, positive terminal will be connected to the source. VGS is also polarity is going to be reverse, negative terminal to the gate and positive terminal to the substrate will be there. So here the layer of the holes, which is P type material, is going to be formed. So it is called P channel MOSFETs are going to be there. When VGS is equal to 0, enhancement type MOSFET is off because there is no conducting channel between source and the drain. The schematic symbol of figure 7-A has a broken line to indicate the normally off conditions. So here you can see that this line, drain, substrate and source, this line is going to be broken here in both the cases, because if there is an inversion layer which is going to be absent, the MOSFET is normally off MOSFET. A gate voltage greater than the threshold voltage creates N-type inversion layer that connects the source and drain. The arrow points to the inversion layer. This acts as an N channel when the device is conducting. So if this is N-type material, N-channel material is going to be, or N-channel inversions layer is going to be formed, then the arrow is going to be inversions. P-type inversions layer is going to be formed, then the arrow is outward directions. So this is the symbol of P-channel MOSFET, this is the symbol of N-channel MOSFET. There are also a P-channel enhancement type MOSFET. The schematic symbol of this complementary MOS transistor is similar, except that the arrow points outward direction as shown in figure 7.2a. With a P-channel enhancement type MOSFET, all voltages and currents are complementary to those of N-channel enhancement type MOSFETs. Now, second point, MOS inverter, MOSFET as a NOT gate. Using a MOSFET, three-way, the NOT gate can be prepared. In this section, we discuss the different way to build an inverter. We use first the MOS driver and passive load resistance. So one way to prepare a MOS technology or MOSFET as the inverter is with the MOSFET devices as the active device and load resistance, passive load resistance will be there, just like RL. Here it is named as the RD. Then two NMOS transistors. Second way it can be divided, which is called active load. Instead of RD, that is a passive load resistance, if there is another MOSFET is going to be used and that will be acting like a load resistance, then it is called active load inverter. And the third way, that is P channel and N channel, both are going to be combined, and that is called CMOS technology, and that way also inverter can be prepared. So the first one is a passive load. How it can be prepared? You can see this circuit 7-3A. This is N channel MOSFET. Substrate and emitter are connected to the grounds. Drain is connected to the VCC positive terminal with the load resistance RD. This is actually passive load resistance is there. Here V0 is going to be 0, VGS is less than VGS threshold voltage, no inversions layer, no conductions, the switch is open, so VDD or VCC will be appear over here, that is cutoff terminal, and the load Q point on the load line will be here, and that means it is at cutoff point, and VD is equal to VDD, that means input is going to be 0, output is going to be VDD. Input is going to be 5 volt or whatever VDD is going to be there, this is greater than VGS threshold voltage, inversion layer is going to be created and hence the current will flow. There is a voltage drop across this IC RL, that is ID into RD will be there. So here the voltage is VDD minus IDRD is equal to VDS, and that is going to be this voltage almost 0. Maximum current will be there. This MOSFET will be in saturations, and so that is the way we can explain the first type of MOS inverter. Figure 7.3a shows a MOS driver and a passive load. In this switching circuit, Vin is either low or high, and the MOSFET acts as a switch that is either off or on. Figure 7.3b shows the load line, which emphasizes the switching action between the saturation and cutoff points. The similar way in a BJT transistor, when Vin is going to be low, the MOSFET is cut off, and the operating point at the lower end of the load line. When V is going to be high, the MOSFET is saturated and the operating point is ideally at the upper end of the load line. Active load. Second type of the inverter now. With MOSFET technology, it is easier to fabricate a MOSFET than a resistor. For these reasons, another MOS transistor can be used as load resistance. We see in figure 7.4, because the gate of the upper MOSFET is connected to the drain. This MOSFET is always conducting. This is a second type of CMOS inverter. Both are N-channel MOSFET only. This MOSFET is known as a driver MOSFET, and this MOSFET is known as a load MOSFET. So this RD, passive resistance, is replaced by MOSFET, because using a MOS technology, it is easier to fabricate MOSFET rather than actual passive resistance from the semiconductor material, and it will occupy less amount of space compared to this resistance. So this is going to be more easier. Here gate is connected directly to the drain, so gate voltage is always greater than VGS threshold voltage. So this MOSFET is always conducting, and that means it offers the resistance between drain and source. So this resistance between the drain and source, that is called RDS on resistance, where the drain and source is going to be on or it is conducting. The resistance offered by them, it is called RDS on. Normally the doping of this device is such that this RDS on is 10 times larger than RDS on of the lower transistor Q2. That is way N-channel MOSFET technology is going to be used. By deliberate design, the upper MOSFET has a resistance that is greater than 10 times the on resistance of the lower MOSFET. For these reasons, the upper MOSFET acts approximately as a resistor, and the lower MOSFET as a switch or driver. Using the MOS driver, that is the lower MOSFET, and MOS load, that is upper MOSFET, leads to the much smaller integrated circuits. They occupy less amount of the room, because MOSFET takes less room than the resistors. This is why most technology dominates in a computer applications. It allows many more gates on a surface of the chip than bipolar technology. In figure 7.4, both the transistors are N-channel devices. Designed like this are as example of N-channel MOS or NMOS technology, which is used a lot for a computer memory chips. So remember now, there are three technology in a CMOS. There is a NMOS technology that is only utilize N-channel MOSFET. That is this type of the technology, That means lower MOSFET as well as upper MOSFET both are N-channel MOSFETs, and they require less room, so more number of gates can be packed on the same semiconductor material, and this is utilized for memory chip devices. That means wherever the memory is required, that N MOSFET technology is going to be utilized. PMOS technology, instead of this, P channel MOSFET is used only, but that technology is nowadays outdated because it requires more power dissipation and it is required a more time also, propagation delay time, and hence it was slower, so it is nowadays outdated. N-channel MOS technology is used for computer memory devices or chips. Third type of the inverter is a CMOS inverter. Now, in CMOS inverter also, there will be two transistors. But before that, you understand these things. When Q2 is saturated in figure 7.4, it has resistance symbolized as RDS on, typically a few hundred ohms. Hence, Q1 is always on, and hence RDS on at least 10 times greater than the RDS on of Q2. So, if this is conducting and this is also conducting, this resistance of this one RDS on, that means resistance offer between the drain and source, is approximately few hundred ohms, and this resistance RDS on is 10 times higher than this resistance. So, that's why this is working as a load resistance. Instead of passive load resistance, it is active load resistance is going to be there. But at that time, both the transistor is on. This transistor is always conducting and this transistor is also conducting. So, there is a current is passing from drain to the source, and because of that current multiplied by voltage, that is the power dissipation, and hence in N-channel MOSFET power dissipation is larger. And to reduce this power dissipation, there is another technology is used, that is called CMOS technology, and Q2 is conducting. The same current flows through each. The product of the current and the supply voltage equal to the power dissipation of the devices with a low output. One way to reduce the power dissipation is with the complementary MOSFETs. For instance, in figure 75A shows CMOS inverter. Notice that Q1 is a P-channel device and Q2 is an N-channel device. This circuit is analogous to the push-pull bipolar amplifier of figure 75B. Because of the push-pull action, one device is normally on and other device is off. Therefore, if Q1 is on, Q2 is off, and if Q2 is on, then Q1 is going to be off. So, this way it is connected. Both the gates are shorted and they are connected as an input, V in, as the input voltage. Here, this is a P channel MOSFET. This is N channel MOSFET. So, Q1 is P channel MOSFET, Q2 is N channel MOSFET. How they are connected? You can see that push-pull arrangement of the transistor. You have studied the complementary push-pull amplifier, right? And in that case, this PNP transistor is upper transistor. This is NPN transistor is a lower transistor. This emitter is connected with the positive terminal of the battery. This emitter is connected with the negative terminal of the battery. Two collectors are common, and that will be the output. Here also, two drains are going to be common, and that is going to be V out. So, this way it is connected P channel as well as N channel MOSFET. At a time, out of this, only one of the transistor is conducting. Either Q1 is on, then Q2 will be off. Q1 is going to be off, then Q2 is going to be on. So, this way either of the transistor is going to be conducting only, and that means it is controlling the amount of the current. These two transistors are in series. So, if both the switch is going to be open, one of the switch is going to be open, that means the current between the drain and source is very few nanoamperes or something, because of the leakage current or minority charge carriers only. and that current is a nanoamperes, and that way the power dissipation is nothing but voltage multiplied by this nanoampere current. So the power dissipation comes in the form of nanowatt. That is the advantage of CMOS technology. When Vin is going to be low in figure 7.5a, this Vin is going to be 0 volt. Which transistor is conducting? Here you can see that P channel MOSFET will be on, because that voltage, source voltage, is greater than gate voltage. So this has a P type inversion layer is going to be on, and hence this is conducting, Q1 is conducting, but this voltage is going to be 0. So gate is 0 and source is going to be 0. So N channel MOSFET is going to be off. So this switch is going to be open between the drain and source. So this switch is going to be closed, but this switch is going to be open. So current is very small, and this switch is going to be closed. So the VDD voltage is appear as output. So V output is equal to VDD voltage. So input is going to be 0 volt, output is going to be VDD voltage. That is going to be high. Another case, if V input is going to be high, that is VDD. So what happens? Upper transistor, gate and source is having the same potential. So this is going to be either you can say the reverse bias or no inversion layer is going to be formed. So Q1 is going to be off, but Q2 is going to be on. So this switch is going to be closed, this switch is going to be open. So VDD is disconnected from the output, but ground is connected to the output. So output voltage V out is equal to 0 volt will be there. So input is going to be VDD, the output is going to be 0 volt. So this way it will work as a inverter. The CMOS inverter, when V input is going to be low in figure 7.5a, Q2 is off but Q1 is on. This means the output voltage is high. On the other hand, V in is high, the Q2 is on and Q1 is going to be off. In this case, the output voltage is low. Since the output voltage is always opposite in phase to the input voltage, the circuit works as an inverter. So this is called CMOS inverter. The CMOS inverter can be modified to build other CMOS logic. So this is a basic logic. Using this basic logic, you can prepare a NAND gate also, you can prepare a NOR gate also, you can prepare AND or exclusive OR gate, etc. Other gates also can be prepared using the same technology. The key advantage in using CMOS device is extremely low power consumptions. Because both the MOSFET transistors are in series, the current is the same through both, but the off transistor is limiting factor because it ideally stops the current. Actually, there is a small amount of the current through the off transistor called the leakage current. Since this current is typically in nanoamperes, the power dissipation is in nanowatt for either output state, whether low or high. The low power consumptions is the reasons for the popularity of the CMOS devices in pocket calculators, digital wristwatch and portable microcomputers. The push-pull connections of figure 7.5a has another advantage over other MOS technology circuits. In either state, the output impedance is only a few hundred ohms. Because of this, CMOS inverter can drive heavier loads than the circuit shown in figure 7.3 and 7.4. So compared to the NMOS technology or PMOS technology or inverter with the passive load, here the output impedance is very low or push-pull arrangement, and hence it can drive a heavier load. So fan out capability is going to be very large with the CMOS technology, and that is another advantage of CMOS over BJT technology. The main disadvantage of the CMOS device is their slow speed. The typical propagation delay time are from 25 nanoseconds to more than 100 nanoseconds, depending upon the particular device. By contrast, standard TTL device have typical delay time of only 10 nanoseconds. Remember that the total propagation delay time equals the sum of the individual delay times. Therefore, several cascaded CMOS gates can really slow things down. For instance, if the four CMOS devices each having a propagation delay time Tp is equal to 50 nanosecond, the overall delay time is of 200 nanoseconds. So the speed of operation of the CMOS is lower. That is the disadvantage compared to the TTL. In TTL, standard TTL is having a propagation delay time is of only 10 nanoseconds. Here it is varying from 25 nanoseconds to more than 100 nanoseconds, and it is additive when number of gates are going to be added. This is the symbol of different type of MOSFETs. The body inward direction arrow is shown. So this is N channel MOSFETs. It can be written like this also, or when this is going to be combined with this one, body with this one, arrow will be showing outward direction just like NPN transistor. So conventionally with the NPN transistor, symbol is made like this one also for N channel MOSFET, opposite to the P channel MOSFET. The body symbol is in outward directions, but when the body and source are going to be connected, symbol will go inward directions. The arrow will go inward directions just like PNP transistor. So this is the symbol of N channel and P channel MOSFET. This is between the gate and source. It will work as an electronic switch. When the gate voltage is going to be 0, the drain and source is going to be open, switch is going to be open. When the gate voltage is going to be VDD, then the switch is going to be closed. So this way it will work as an inverter. This is N channel MOSFET, this is a P channel MOSFET. The direction of conventional current is shown. N channel MOSFET, it is from the drain to the source conventional current. P channel MOSFET, the direction of the current is in opposite directions. Now, whatever we have learned in a fourth edition of Malvin-Ullrich, in this seventh edition of the Malvin-Ullrich, it is given in this way. Actually, it is the similar things, but more detailed it was explained in a fourth edition. That's why I have taken from the fourth edition also, and I have given the input from the seventh edition also. We can read it from here. A voltage is applied between the gate and source. The switch is closed and the current is allowed between source and drain. The transistor is on. The voltage between the source and drain across a closed switch is going to be 0. Since the MOSFET is available in two polarity, N channel and P channel, the polarity of the applied gate source voltage must be as shown in the figure 14.6c. For the N channel transistor, the gate must be more positive than the source. That means VGS must be positive. The opposite is true for the P channel MOSFET. That means the VGS threshold voltage should be negative in P channel MOSFET. The current through the N channel transistor must be from drain to the source as shown in the figure 14.6c. For the P channel transistor, the current must be from the source to the drain. Notice that the current is in the direction of small arrow on the drain, a good memory crunch. This polarity and current directions are important. You should make every effort to commit them in your memory. Now related with this one, there is a small example. Example number 4. An N-channel MOSFET can be used to construct a simple inverter as shown in a figure 14.7. Determine the current I and output voltage V2 if A, V1 is equal to 0 volt DC and B, if V1 is equal to plus 5 volt DC. Solution. If V1 is equal to 0 volt DC, there is no current in 100 kilo ohms resistance. Thus, the gate to source voltage is 0, the MOSFET is off, the switch is open, the MOSFET current and the current in 10 kilo ohms resistance are going to be 0. The voltage V is equal to 5 volt. And second thing B, if V1 is equal to 5 volt DC, the gate is more positive than the source. VGS is greater than VGS threshold voltage, there is an invergence layer is going to be there and MOSFET is going to be on. The switch is closed, V2 is going to be 0. The MOSFET current is going to be 0.5 ampere, voltage upon resistance, 10 kilo ohms resistance. So that is going to be 0.5 milliamperes. This circuit could be used to implement the basic inverter introduced in the chapter 1. The small size of the MOSFET on the IC is one of the greatest advantage of ICs constructed using MOSFET. The 10 kilo ohms resistance in figure 14.7 requires a large area on an IC compared to the MOSFET. That's why if LSI, large scale integration circuits, VLSI and super LSI, that means very large scale integration circuit, more than 1000 gates for the chip, more than 10,000 gates for the chip, or microprocessor chip, etc., where number of gates are required very large, then it is better to utilize CMOS technology rather than TTL technology, because they require less amount of the room, so more number of gates can be packed on a same amount of chip. A second MOSFET can be used in place of this resistance as shown in the figure 14.8. In this case, the transistor Q1 has its gate connected directly to the drain. This is called with the active load. When it is connected in this fashion, its behavior is similar to the resistors, but it shows little non-linearity compared to the passive load. Q1 is called the active load, and this circuit is simple inverter that we have seen. This is the inverter with the passive load 10 kilo ohms resistance. V1 is going to be 100 kilo ohms resistance. So if this is voltage is going to be 0 volt, VGS is less than VGS threshold, no current will be there. So 5 volt will be appear over here. So V2 is going to be 5 volt. If V1 is equal to 5 volt, 0, then this is going to be conducting, the voltage will be drop here, and V2 is going to be 0 volt. This is inverter with the active load. This passive resistance is replaced by MOSFET. The gate is directly connected to the drain, so upper MOSFET Q1 is always on. So this is also N channel MOSFET, this is also N channel MOSFET. So with the NMOS technology, this is work. Now the third type of things, complementary metal oxide semiconductor field effect transistor. ICs constructed entirely with N channel MOSFET are called NMOS ICs. ICs constructed entirely with the P channel MOSFETs are called PMOS ICs. The 74C00 and 74SC00 families are constructed using both N channel and P channel MOSFETs. Since the N channel and P channel MOSFETs are considered complementary devices, these ICs are referred to as CMOS ICs. In a TTL series, 7400 series, but here it is 74C00 series. That means here the active device is MOSFET is used. HC means stand for high speed CMOS, remember. The CMOS inverter is shown in figure 14.9. Ideally, the characteristic of the N channel are closely matched with the P channel. That means a normal transistor PNP and NPN, HFE is taken almost similar way here. P channel and N channel MOSFETs are having closely matched characteristic is going to be there. This circuit is the basis for the 74C00 and 74HC00 families. Here is how it works. If V1 is equal to 0 volt DC, the N channel MOSFET is off and QP, that is P channel MOSFET, is on, and VC, output voltage V0 is equal to 5 volt DC. Second, if V1 is equal to 5 volt DC, N channel MOSFET QN is on, QP is off, and V2 is equal to 0 volt DC. This is a P channel MOSFET, this is N channel MOSFET, both are connected in complementary modes. This is the source is connected with the positive terminal. Here the source is connected with the negative terminal grounds. This is the input voltage, this is going to be the output voltage. When this is going to be 0, this MOSFET is going to be off and this MOSFET is going to be on. So 5 volt will be appeared here and output is going to be high. When V input is going to be high, that is 5 volt, this MOSFET is going to be on, QN is going to be on. So this switch is going to be closed. So ground voltage is appear at here, so output voltage will be low and this switch is going to be open. Note that in the steady state, while not switching, one of the transistor is always off. As a result, the current I is equal to 0 milliampere. So either the output is low or high, that is steady condition. Out of these two transistors, only one of the transistor is conducting, other transistor is off, that is limiting the current and hence the output current is almost 0. When the switching between the state, both the transistors are on for a very short time because of the rise or fall time of V1. This is the only time the current I is non-zero in the devices Q1 and Q2, both are on for a fraction of the time only, and that creates some output currents. This is the reasons why CMOS is used in application where DC power supply current must be held to minimum, like wristwatches, pocket calculator, etc. A word of warning: if the input voltage V1 is held at plus 5 volt divided by 2, that means 2.5 volt DC, both the transistor will be on. N channel MOSFET is also on and P channel MOSFET is also on. That means it is a short circuit between the power supply, positive terminal as well as negative terminal. This is almost a direct short between plus 5 volt DC and ground, and it won't be long before both the transistor may expire. So don't impose this condition on a CMOS IC. So remember, you have to careful that input voltage should not be VCC by 2 or VDD by 2. Otherwise, both the transistor will be damaged. This is some assignment is given for this particular lecture. You can do this assignment and you can submit it also. I will give you the quiz also later on. So how does the LED differ from ordinary silicon diodes? What are the two type of BJTs? What is complement of N channel MOSFET? Sorry, an NPN BJT is on when its base is more positive or negative than emitter. What is active load in NMOS technology? Thank you very much, friends.